Welcome back. A statistical test is a little bit like a proof by contradiction in mathematics. We start by assuming something, and typically what we assume is not what we want to show. In fact, it's often the complete opposite. And then we do some work under that assumption, and we end up with a contradiction, or something that is obviously wrong. So as a result, we conclude that there must be something wrong with our original assumption. In statistics, we have to deal with the natural variability that's associated with our data. So there's uncertainty associated also with obviously wrong. And for us, obviously wrong will mean unlikely in a probability sense. In this video, we'll outline some of the steps and structure of a statistical test, and we'll introduce some of the vocabulary that is used. In statistics, tests are used to answer direct questions about the theoretical world, and the goal is to determine whether the data provide enough evidence for us to believe a claim about the population or theoretical world. Statistical tests are often called hypothesis tests or tests of significance. There are very subtle differences between these two phrases, but they're so subtle that we won't worry about them. A direct question we might want to answer with a test might be something like, is a beer cap, like a coin, equally likely to come up on either side when flipped? Or, after a facelift, does the perceived age show that people look younger? Or, is the mean healthy body temperature for a human 37 degrees Celsius? The first step of a statistical test is to formulate an hypothesis to test and specify an alternative to that hypothesis. Throughout this video, I'm going to use a court case as an analogy to a statistical test. Many legal systems around the world are based on the presumption of innocence, often referred to as innocent until proven guilty. We presume that our starting point is that anyone charged with a crime is innocent, and the burden of proof is on the prosecution to prove otherwise. In statistics, the presumption of innocence corresponds to what we call the null hypothesis, written as H subscript 0 and typically said H naught, where naught here is nothing or zero. The null hypothesis says that nothing is happening. That is, it's the status quo, or there is no relationship, or there are no differences. We use the null hypothesis as a working hypothesis. We assume it is true and see if our data are likely under that assumption, or if they contradict it. Usually in a court case, we're trying to show that the defendant is guilty, and that corresponds to our alternative hypothesis in statistics. Sometimes the alternative hypothesis is called the research hypothesis because it's what the research wants to show. The alternative hypothesis is written as an H with a subscript, a lower or uppercase A. That's the notation I prefer. Some people like to write it as H with a subscript 1 in contrast to H sub 0 for the null hypothesis. Like the prosecutor who wants us to conclude that the defendant is guilty, we typically want to prove that this research or alternative hypothesis is true. And the way to make that conclusion is to see if we have enough evidence to rule out that any differences from the null hypothesis could be due to chance. So an important first step in any statistical test is to carefully define what our null hypothesis is and what the alternative is. As an example, if our goal is to show that facial plastic surgery reduces the mean perceived age, our null hypothesis would be that nothing is going on. So we'd assume that the mean perceived age change is 0, and our alternative would be that the perceived age change is positive. That's assuming we're calculating age change as the perceived age before minus after surgery. That's an example of a one-sided alternative. We're only interested if the mean perceived age change is positive, meaning patients look younger. We can also have two-sided hypotheses. In our beer cap example, if we're interested if it's 50-50, we'd be interested in whether the chance of getting reds is greater than a half or if it's less than a half. So then we'd use a two-sided alternative corresponding to not equal to a half. In most situations, two-sided tests are appropriate, and if you're ever in doubt, use a two-sided test. The first step in any statistical test, then, is to clearly specify what the null hypothesis is and what the alternative to it is. In a court case, we need evidence collected by the police and prosecution, which brings us to our second step. The second step in our statistical tests is also to put together the evidence. In statistics, the evidence is provided by our data. In order to make the data useful, we have to summarize it into a statistic called the test statistic. Like any statistic, the test statistic is a numerical summary of the data. But what differentiates a test statistic from just any statistic is that it is formulated assuming that the null hypothesis holds. This is important to remember in statistical testing. We make an assumption, H0, our null hypothesis, and we then work as if it is true. So as an example, if we assume that a facelift doesn't lower the mean change in the perceived age of a patient, then we construct the test statistic under the assumption that the mean age change is 0. So our second step is to accumulate some evidence. That is, collect some data, summarize them into a test statistic, always assuming that the null hypothesis is true. Once the evidence has been collected and summarized for the judge or jury, they have the responsibility of careful deliberation. They need to decide if the evidence is overwhelming enough to reject the presumption of innocence, beyond a reasonable doubt. In statistics, the tool for deliberation is a p-value. A p-value transforms a test statistic into a probabilistic scale. It is a number between 0 and 1 that quantifies how strong the evidence is against the null hypothesis. If the evidence is not beyond a reasonable doubt, that means that chance, or the natural variability we expect, is a reasonable explanation for anything we see in our data that is not consistent with what we'd expect if the null hypothesis is true. To decide whether the results could just be due to chance, we ask the question, if the null hypothesis is really true, how likely would it be to observe a test statistic, our summary of our data, of this magnitude or even larger, just by chance? The numerical answer to this question is the p-value. The smaller the p-value, the more unlikely it is that we observe our data, assuming the null hypothesis is true. So the smaller the p-value, the stronger the evidence we have against the null hypothesis. A p-value is not a measurement of how likely it is that the null hypothesis is true. The null hypothesis either is true or isn't true. We may not know which it is, but we can't put a probability value on it because it's not random. What a p-value does tell you is how likely the observed data would be if the null hypothesis were true. It's a measure of the strength of the evidence against the null hypothesis, and the smaller the p-value, the stronger the evidence. So our third step is to determine how unlikely the test statistic is if the null hypothesis is true, and this is our p-value. And finally, we have the verdict. Our judge or jury has one of two choices. They could decide that the evidence is not strong enough to convincingly rule out that the defendant is innocent, and they'd conclude not guilty. In statistics, not strong enough evidence means the p-value wasn't small, and we conclude that our data are consistent with the null hypothesis. We can't conclude H0 is exactly true, but we can't reject it either. Or our jury could decide that they are willing to rule out the possibility that an innocent person stacked up this much evidence against them, and then they'd reject the presumption of innocence and conclude that he or she is guilty. The corresponding situation in statistics is a small p-value. We have data that are unusual enough that we are willing to rule out that the null hypothesis is true, and by chance we got the observed data that we did. In this case, we have a small p-value, and we reject the null hypothesis, concluding that we have sufficient evidence against it and that the alternative hypothesis must be true. In this case, we say we have a statistically significant result. At this point, you may be wondering how small is small for a p-value. 0.05 or 5% is a very common cutoff for small, but it's a little bit arbitrary. If we get a p-value less than 0.001, That can be considered strong evidence against the null hypothesis. Larger than that, but less than 0.01, is still pretty good evidence against the null hypothesis. And after that, it starts to get a little bit gray. Between 0.01 and 0.05 is considered small enough evidence to say the null hypothesis is not true in many situations. In other situations, even getting a p-value between 0.05 and 0.1 is enough evidence to conclude that the null hypothesis isn't true. When we get one of these larger values for our p-value, the evidence against the null hypothesis isn't as strong. And if we get a p-value greater than 0.01, that means that if the null hypothesis is true, what we've observed in our data is something that happens 10% of the time. Then we conclude that our data are consistent with the null hypothesis. Depending on the context of the problem, you might be willing to accept a larger or a smaller p-value. If concluding that you have a statistically significant result is going to incur a lot of expense or possible discomfort for people, then you'll want a smaller p-value than if the consequences of a statistically significant result aren't quite so expensive or inconvenient. So the final step in a statistical test is to make a conclusion based on our p-value in the context of our problem. To summarize, here are the 4 steps of a statistical test. In the upcoming lectures, we'll apply them to real data and real questions.